All right. Hi. We're going to talk about the consumer utility maximization problem, go over kind of the key concepts, and work through a kind of an extensive numerical example. So, we'd all know the issue, right? As consumers, we have a fixed amount of money that we can spend, our budget, and we want to get the most return possible, right? We want to generate the most happiness or utility that we can with those limited funds. So, technically, the consumer's problem, right? Finding the optimal affordable consumption bundle, right? That's just the list of goods and services that we consume on a period by period basis that, again, maximizes our total happiness, right? And of course, the reason why we can't have infinite utility or happiness, right, is that we have that fixed budget and we can't get goods and services for free, right? So we have the prices that we have to pay. Okay. Now, what's going to determine, given those prices and budgets, how one consumer reacts differently from another is going to be our kind of individual preferences, right? One unit of consumption of a product might give me more happiness than you, and that might lead to a difference in how we decide to allocate, right, the same budget and the same across the same prices. Again, the way to think about it is, at the beginning of a period, the beginning of the week, and you're trying to decide, right, what quantities of all the products are out there that you want to consume. Every time you change that list a little bit, you buy a little bit more of this and a little bit less of that. Well, that's going to affect the total amount of benefits or happiness or utility that is going to be generated, that you're going to receive. And we like to think, right, mathematically, there is a unique combination of goods and services that we consume every period that would give us the highest possible value of utility or welfare or happiness, right? And it's that kind of elusive goal that we're trying to accomplish here. What are the rules that a consumer can follow to get as close as they can to that optimal bundle, that utility maximizing use of their fixed resources? And the way we're going to get there is not so much thinking about that idea of, okay, we want to get to the top of this mountain of utility. We want to get to the highest point possible of total happiness. That is where we want to go. But it's easier to solve the problem in thinking about it as a step-by-step process. Right? So that's the idea of marginal analysis. Thinking about how we allocate each dollar, right? Each transaction that we make, we want to make sure that we're getting the most return possible at the marginal level. And the cumulative effect of all of these marginal optimizations will be the top of that heap, right? The top of the utility function. Right? And we've seen this before, right? When we talk about a marginal value, excuse me, it's the change in the total value incrementally. So in this case, since we're talking about utility or happiness, marginal utility, MU, will be defined as the change in total utility due to a change in consumption. Again, it's just saying, how much benefit do I get for that one extra unit consumed? And mathematically, we would express it thusly, right? So MU equals delta TU, the change in total utility for each additional unit consumed. So when you think of that delta Q, think of it as just being one, right? You spend one more hour at the gym. What's the return? You buy one more movie ticket per week. What's the change in utility? Right? So we also have a very particular concept of how total utility and marginal utility relate to consumption. Right? And the expectation is that we're going to be following the law of diminishing marginal utility, that we experience diminishing returns to our happiness as consumption increases. Okay? And that's going to look something like this, right? So holding everything else constant, past a certain point, we are very confident that each additional unit consumed, each delta Q, will add less to our total happiness, our total utility, than did the previous unit. Right? We keep consuming the same additional units of the same good, And that step up, that climb, right, that we're going to get is going to be smaller and smaller and smaller. So even if we're getting additional benefits, right, the change is going to get smaller and smaller. Our total happiness might be rising, but at a diminishing rate. And so the other equivalent way of saying that is that our marginal utility, the additional gain, falls as consumption increases. All of those are equivalent statements here. And just to cover all the bases, right? It's definitely possible to have a good or a service such that you are going to experience increasing utility for a limited amount of time, right? That the first unit gives you some utility, the second gives you even more gain, the third even more, but eventually we all know, right? We're gonna hit that wall. We're gonna start to get diminishing additional utility. So that's the idea. We don't know where it's gonna happen, but for every good or service, eventually this diminishing rate of increase is going to kick in. So just to think of some numbers, right? And I think we've seen this example before. So let's imagine that we are tracking my utility levels on a given day as I consume additional units of coffee, right? So each one of these values of Q, just think of this as increasing the coffee consumption over a given day. And we track it from 0 to 5. So of course, keeping in mind that TU, our total utility, right? This is specifically tied to the consumption of this product, right? So it's not measuring, my total well-being. It's just utility welfare derived from consumption of coffee. So what that means, of course, is if I'm consuming 0 coffee, I'm deriving 0 happiness from coffee consumption. So we'll be at that 0 point. And then as my consumption increases, my total cumulative happiness or utility is going to be increasing as well. So this middle column here, this is tracking that mountain, right? That total level of utility. And what the law of diminishing marginal utility tells us is that these changes, right, these increases for each change in quantity are going to get smaller and smaller, right? So the first cup of coffee brings my happiness from 0 to 8. So the delta TU is going to be 8. The second unit brings me from 8 to 16. So I add 6. There's the delta, there's the change, 6, so on and so forth, right? So from 14 to 18 for the third, I'm still getting additional happiness, but again, it's less and less of a gain each time. And then finally, from 3 to 4, we go from 18 to 20. So I've added 2. And then once we hit that 5th unit, we hit a plateau. We're at the top of the hill, and it's flattened out, and my marginal utility has gone from diminishing to diminished down to 0. Right? So I get no additional happiness for that 5th cup of coffee. So the mathematical pattern that we've developed here are these total and marginal functions. Right? So this graph on the left plots out our total utility versus consumption. So again, that's the rise and eventually the plateau. So again, from 4 to 5, we stayed at 20. And then the changes each step of the way, again, went from the 8 to 6, 4, 2, and then finally down to 0 when our line is flat here, right? So the other way, right, the pure mathematical way of thinking about this is that the marginal utility for each unit is just tracking the slope of our total utility, right? So it's rise over run of 8 over 1, marginal utility of 8. Rise over run 6 over 1, marginal utility of 6, so on and so forth. We go up by 4 and over 1, up by 2. So as that line flattens out here at a constant rate, it doesn't have to be that clean and linear. But that's the other way to think about how we're deriving this, right? But from our point of view, it's more important about what it's telling us, right, in terms of consumer behavior. And taken together, these two graphs are kind of a representation of an example consumer's preferences. So now all we have to do is combine the information here with the information in our previously constructed budget constraint model, right, which tells us what we're capable of doing. This tells us what we want to do. Where those two meet is going to give us the optimal bundle, the solution to the consumer's problem. So now that we have all this information, let's kind of put it all together. So there's a very simple, quote unquote, rule of utility maximization or optimization that we can imagine our example consumer following to, right, again, answer that consumer's problem question. How best can we allocate my scarce resources, my budget? And it comes down to that marginal value once again, right? So the simple rule is with each transaction, each dollar, each unit of currency that we spend, we want it to go to the unit of consumption that gives us the highest utility gain, the marginal utility per dollar spent, right? So we can't just look at the utility. It's got to be, right, the benefit versus the cost, right? So it's utility per dollar spent. So we're controlling for essentially that price variable, right? So again, kind of the silly example, if we were just trying to figure out where can I get the most utility, right? We would say, oh, I could buy a car and get and receive $50,000 of happiness out of having that new car. Or I could buy a cup of coffee and I would only get 4 units of utility out of it. Well, that's apples and oranges, right? Because the car obviously is going to cost you way more. So we have to control for that. We have to factor that in. Okay. So we follow this rule, dollar by dollar, transaction by transaction, purchase by purchase, until all of our money's gone. That means we've hit that budget constraint. But if each step along the way, we have maximized utility per dollar spent, the resulting attainable, efficient bundle of goods will be utility maximization. Sorry, will be utility maximizing. That's what I meant to say. Right? So that will answer the question of all the attainable, efficient bundles out there, everything that we can afford on that budget constraint, which one is going to give us the best outcome? It'll be the result of this process. So let's walk through a full example here. So let's start with the budget information, right? So again, say on a daily basis, we've got $10 to spend and we can spend it either on coffee or donuts. Each cup of coffee costs $2. Each donut, say, costs $1. So we could put that together to draw the budget constraint. We'll get to that in a second. On top of that, we add our utility information, right? So this is the same columns that we've already seen. So these are the total and marginal utilities for coffee. Over here, we have the same functions, total and marginal utility across the same, right, 5 units of consumption, but now applied to donuts, okay? So we see diminishing marginal utility at work, right? So we add 2 units for the first, 1.5 units of utility for the second, 1, and then 0.5, and then 0. Okay, so that's where our marginal utility values come from. But we can't just compare marginal utility from one good to the other. It's got to be utility gain per dollar spent, right? So that's where these columns come from here. We simply take the price, in this case, the price of coffee of 2, and divide that into the marginal utility, right? So the 4 is coming simply from the marginal utility 8 over the price of 2. And that price is going to stay the same all the way down, right? So second unit gives me 6 units of utility divided by 2 gives me 3 units of utility per dollar spent. 4 over 2, 1, 4 over 2 is 2, 2 over 2 is 1, 0 over anything is 0. Right? And then our relevant column in the competing good, our donuts, we will construct exactly the same way. We will take our marginal utility and divide by the price, very conveniently in this example, set to 1. So it's just 2 over 1 gives us 2 units of utility per dollar spent, so on and so forth. So we just divide all these by 1 and just repeat the numbers over here. So now we have all the information we need to walk through that little kind of optimal shopping trip scenario, right? I've got the $10 in my pocket. Where do I want to spend it? So what I've done in this table, right, just taken those relevant columns, right, the marginal utility over price for coffee and donuts, and that's what our imaginary consumer is going to need. Okay? So put ourselves in the consumer's point of view. I haven't purchased anything yet. I have all $10 to spend. Where do I want to make the first transaction? Well, remember the rule of optimization. Each transaction should maximize marginal utility per dollar spent. So I can either get 4 units of utility per dollar or 2. 4 is bigger than 2, so I'm going to buy a cup of coffee first. Right? So that's going to be our first transaction. First purchase is a first cup of coffee, and it costs us $2. So we got to keep track of our spending, right? Because we can only do this until our budget is exhausted. Now, here is the trickiest step of this process, right? Is recognizing that once we purchase and consume that first unit, we can't get that same level of utility again, right? So now the comparison, right, that first cup of coffee is gone. Now the comparison is between the second cup of coffee, which still gives us 3 units of utility per dollar, and the first donut. Okay? So we can just say, well, which one's bigger, right? Follow the rule, maximize utility per dollar. So we're going to buy another cup of coffee before we've bought a single donut, right? So our second purchase is another cup of coffee. We've spent another $2. So keeping track of our total spending, it's now $4. But this second cup of coffee is now also off the board, right? So now we come back and we say, well, I still have some money to spend. What should I do? The utility per dollar is equal between the third cup of coffee and the second donut. So there's no wrong answer between the two, but just to mix it up, let's imagine our consumer makes that third purchase, their first donut, and they spent $1. So total spending is now $5. We get the idea. We just keep going, right? That first donut now is gone. So now we compare third cup of coffee and second donut. 2 wins out over the 1.5. So our next purchase is going to be a third cup of coffee, bringing our total spending, adding $2 to our total spending. So bringing it up to 7. And now we've got fourth cup of coffee or second donut. The 1.5 from the donut wins out. And our fifth purchase, our second donut, add another $1 to our spending to bring it up to 8. So that guy's off the board. Now we have third donut versus fourth cup of coffee. Either way, you get the same utility. Just to make it, even here, make it to come out our consumption bundle on a whole number. Let's imagine the consumer buys that fourth cup of coffee because they have $2 left to spend, and they spend it all on that cup of coffee. And that'll be the sixth and final purchase, fourth cup of coffee, spent $2 more, bringing our spending up to $10, which was our budget. So now we have this consumer's daily optimal bundle of coffee and donuts, 4 cups of coffee and 2 donuts. Okay. Obviously, this is a kind of a silly, trivial example, but the steps, the logic, the intuition holds, right, for the non-trivial case where I am a real consumer with real money and I need to make real decisions. These are the same concepts, right? If you allocate each dollar, make each transaction such that you get the most utility per dollar spent, when your budget is exhausted, you will be at the optimal point. Okay? So just to kind of finish out the example here with this optimal bundle, once again, what we've done is found the best place to be on the budget constraint. So remember, we have the $10 to spend. Coffee was $2 each. So if we spent it all on coffee, we could purchase 5 units. So that's that y-intercept. All $10 spent on donuts, which cost $1 a piece, would give us that maximum consumption of 10. We want to just kind of double check that the bundle that we found is actually on the budget constraint. So the equation, right, for the budget constraint, quantity of coffee equals 5, our y-intercept, minus price of donuts over price of coffee, the slope, times the quantity of donuts. We plug in 2 for our quantity of donuts, and that gives us 5 minus 1/2, 2. We can still afford 4 cups of coffee if we purchase 2 donuts. So the bundle for coffee and 2 donuts is in fact affordable, and it puts us right here on our budget constraint. Okay. So thinking like of an exam type question, right, on this topic, if we flip this all around, and if I just showed you this graph and I said, oh, a consumer decided to be here, how did they get there? Why did they make that choice, right? You should be able to say, oh, based on their preferences and their optimization procedure, they found this to be the utility maximizing point. And that's kind of how it operates, right, in the real world, right? We never see somebody's table of marginal utilities per dollar spent. All we see is what they do, right? So it's kind of your preferences as revealed by your behavior. And you wouldn't have purchased 4 cups of coffee and 2 donuts if you didn't find that to be the optimal point. That's the assumption anyway. Okay. Okay, so that's kind of how the rule plays out when we have, again, the simplest possible case. You're either buying X or Y, and we want to find the combination of those 2 products that give us our utility maximizing point. What would this look like, however, in a case of more than 2 goods, again, in the more realistic scenario? Okay. Well, the rule that we've laid out and kind of the logic of this process implies that we want to have that ratio of marginal utility to price equalized across all the goods that we're consuming, right? We want to try to get as close as we can to the point where we're getting the same utility per dollar from every transaction that we make. So the end result should come from something like this, right? For good 1, marginal utility for good 1 over the price of good 1, that should equal the same value for good 2, the ratio of utility gained to price. Good 3, oh, sorry, that should be a 3. Marginal utility of good 3 relative to the price of good 3, those should all be equalized. Again, the utilities are going to be different across goods. The prices are going to be different across goods. But what we can control is our levels of consumption. Right? So the logic is, if this doesn't hold, right, say if for whatever reason MU3 over P3 is higher than all the rest, well, basically what that's telling you is you didn't do, right, you didn't follow the optimization correctly, because the bundle that you've consumed should have contained more of good 3, because you could have earned more utility per dollar. So when you readjust, you're going to spend more of your money, make more purchases on good 3, because that's where the higher utility per dollar is, and diminishing returns is going to drive down that marginal utility, right? And you're going to keep doing that until it's equalized. And same thing in the other direction, right? If for whatever reason, at the end of the day, you kind of look back and you say, wow, gosh, where I ended up, my marginal utility per dollar on good 2 was lower than everything else. Well, when you go back and re-equilibrate your bundle tomorrow, you're going to say, I'm going to buy less of good 2 because it was giving me less utility per dollar than the other options I had. And as you scale back on consumption, right, you're going to be moving back up to the left along that marginal utility. Marginal utility is going to start to rise. So this is one of those cases where I think the logic of this rule of equilibrating, equalizing utility per dollar is easier to see in the case when it's not true, right? What does it mean when this doesn't hold, utilities too high or too low? The obvious adjustment, right, is going to be buy more of the utility of the good with a high utility, less of the good with the lower utility, and that'll lead you back towards this equality. All right, so now what we've done so far is got to the point where we can find an optimal bundle on a stationary, static budget constraint, right? But things always get more interesting when we say, well, what happens when things change, right? So we can use exactly the same rules and logic to trace out the optimizing consumer's reaction to a change in the price of a product. And this should sound familiar, right? Well, modeling how a consumer reacts to the change in the price of a product, that's a demand curve. And if you were thinking that, you are right. And in fact, what we're going to show is through this process, we can derive from first principles, from scratch, why a demand curve looks the way it does. So let's walk through this. So again, imagine our consumer, they've solved the problem. They're at their optimal bundle day after day, week after week. They're buying their best combination of goods. In our little example, that's 4 cups of coffee and 2 donuts every day. That doesn't sound real healthy, but we'll stick with that, right? And they're happy with that, right? If nothing changes, their budget doesn't change, their preferences don't change, prices don't change, they're going to do that same thing day after day after day. But now let's mix it up. Let's imagine that the price of one of those goods increases. From our example, let's imagine the price of donuts goes up, say from $1 to $2. The consumer is going to react to that change for 2 familiar reasons, right? The first is simply, right, well, if the price of a product goes up, I can't afford to buy the same number of units that I used to. That's the income effect of a price change from the pivot inward as price goes up of a budget constraint. The old bundle is now outside the new budget constraint, so I have to react. I have to cut back on consumption. The other reaction is going to come from our rule of optimization, right? Even if our preferences haven't changed, our marginal utilities are the same. When the price goes up, utility per dollar comes down. And if our ratios were equalized, now they're not, right? Now, one good is going to give you more utility per dollar than the other, and that's going to lead to a reshuffling of your optimal bundle. It's going to lead to a new outcome of that little transaction by transaction optimization. And that shift, consumption of one good to the consumption of the other in response to a change in utility per dollar, that's the substitution effect. So the combination of those two, I can't afford to buy what I used to buy, and I'm going to reshuffle my optimal bundle. The total change in consumption is going to be the movement along the demand curve, which again, we're quite familiar with, but now we can see it again, kind of decomposed within that budget constraint framework. So let's kind of dig into that. So look at that kind of rule of optimization with only 2 goods, right? We have good 1 and good 2. And if we're at that optimal bundle, we should be as close as possible to this equality, right? We should be getting the same utility per dollar from each good 1 and good 2. But now imagine that the price of good 2 decreases. Okay? Price of good 2, P2 comes down, such that the new price, call it P2 prime, is less than the original price, P2. So as that price comes down, the utility per dollar goes up because you're getting the same utility and spending less money for each unit. So now we have an inequality here. Marginal utility per dollar for good 2 is greater than that for good 1. And we know how to react to that. We reallocate our transactions, right, toward good two, by less of good one, more of good two, and that's the substitution effect, irrespective of the budget shift at this point, right? Just looking at this optimization. So that's when the price decreases, we should be able to see, right, it's going to go the other direction. If prices go up, start with that equality, but now price of good two goes up. And just to make our notation consistent, the new price level is P2 double prime, some number greater than where it started. So now you're getting the same utility that you did before, marginal utility of good two, MU2, but it's costing you more to get it. So the ratio, utility gain per dollar spent, comes down. And now you're going to reallocate towards good one, away from good two. There's the substitution effect in the other direction. Okay, let's see this at work. So we're going to go back to the same example. Everything's exactly as it was, except donuts now have a new price level, PD prime. It used to be PD of $1, now it's PD prime of $2. So our nothing changed on the coffee side of the ledger here. Total utility is the same, marginal utility is the same, price is the same, so MU over P is the same. And on the donut side, we like donuts just as much as we did before. So total utility and marginal utility are the same. The only thing that changes is we are now dividing this by 2 to get our MU over P, right? So all of those values in the last column are cut in half from what they were before. But we still have our $10 to spend. Let's walk through the little shopping transaction by transaction process here. So again, same thing. We're just looking at the relevant columns, marginal utility per dollar for coffee and donuts respectively, with the new price level here. And sorry, that should be PD prime here. Okay. And clearly, right, things are going to change, right? So just kind of fast forwarding through what we know is going to happen here. 4 is bigger than 1, so I should buy a cup of coffee. 3 is bigger than 1, I should buy a second cup of coffee. 2 is still bigger than 1, I should buy a third cup of coffee, right? So I've bought 3 cups of coffee now before I even glance in the direction of a donut. But now that those first 3 cups of coffee are off the board, the 4th cup of coffee and the first donut, there's a 1-to-1 tie. So again, there's no, doesn't matter what order you go in, but let's say we finally go buy a donut. And now we've bought 3 cups of coffee and a donut. Each one of those transactions costs $2. So our total spending is now up to 8. This guy is off the board. So now our remaining $2 can either go to a cup of coffee, 4th cup of coffee that gives us $1 of utility per dollar spent, or the second donut that only gives us now 75 cents of utility per dollar spent. So it's going to go to that 4th cup of coffee, bringing our total expenditure up to our budget of 10. And this gives us a new optimal bundle. It used to be 4 cups of coffee and 2 donuts. Now it's 4 cups of coffee and 1 donut. So not a, just because of the numbers we chose, not a wild substitution going on here, but what we see is a reduction in consumption at the optimal bundle in reaction to that price change, in this case, the price increase. So again, all of this exercise is an exact repeat of the steps, the logic that we saw before, just in reaction to a change in price. So here's where it gets good, right? Trace out what we've done here, right? So this, the first line here, the blue budget line going from 5 to 10, that was our original budget constraint, $10 spent on the coffee, $2 per unit, or donuts, $1 per unit. And what we saw, we had an optimal bundle here at point A, 4 cups of coffee and 2 donuts. Now, when the price of donuts goes up to PD prime of $2 per unit, the intercept doesn't change, the y-intercept doesn't change, but the line becomes twice as steep, right? And now, obviously, if we spend all $10 on donuts that cost $2 each, our intercept is going to be cut back here to 5. So this red budget constraint, that's the new reality for the consumer after that price goes up. That's the pivot inwards. So we immediately recognize we can't stay at point A. It's now outside our new budget line. It's unaffordable, unattainable. So we go through the re-equilibration of that little shopping trip. And what we found again was 4 cups of coffee, but only 1 donut at point B. So that's our new optimal point. And just to verify that that is on the new budget line, right? We plug in 1 donut, 5 minus 1 gives us enough money to spend to get 4 cups of coffee. So that is in fact on our new budget line here. So finally, look at this. What does that give us? It gives us 2 consumption levels at 2 different prices. We line those up and connect the dots. We have a demand curve, right? And that's exactly what we've done, right? So remember point A, that was at the original price level. And this is for donuts, right? That's what's experienced the change in price. The original price level was $1 and our optimal consumption was 2 units. Then the price went up to 2. We recalculated our optimal bundle and we found that we would buy only 1 unit. Those 2 points are both optimal price quantity combinations for this consumer. And that reflects their demand relationship, right? That movement from point A to point B. So it's kind of fun to walk through an example like this and get to this point. It's very satisfying, right? To say, oh, after all that, a demand curve is downward sloping. But now I think we've got a much better insight into what's happening as we move along any consumer's demand curve. We have kind of a much fuller story of what's happening, right? And the idea is every point on a consumer's demand curve represents the outcome of that optimal bundle search, right? That behind the scenes is a marginal utility per dollar spent calculation and a transaction by transaction optimization process, right? And not only are they thinking about the good in question, right? Price of donuts versus quantity of donuts. It's the allocation across all the different goods that we can possibly consume. In this case, donuts versus coffee, right? But they all go into that decision, right? So the marginal utilities and the prices of all goods potentially go into our decision about the optimal outcome for one good. One demand curve is inextricably linked to every other demand curve. Okay. So think about what we just saw, right? That movement along our demand curve, price goes up or price goes down and we react. It's an entire recalibration of that optimization process. And we might be buying more of good X when the price of Y goes up or less of good X when the price of Y goes up. We might not react at all. That's going to be reflected in our cross price elasticities, right? How strongly are 2 goods related as substitutes or complements. That all comes out of this calibration, this optimization process. Okay. So going forward, be able to walk through an example like this, right? If I give you a budget and prices and total utilities, you should be able to go through the rest of it and get to the optimal bundle and show it on a budget constraint. And then we throw a price change in there. Price of one good might go up, it might go down, re-equilibrate, recalibrate, and we should end up with a demand curve that's being derived in the process. It's always going to look effectively just like this, right? The goods will be different, the numbers will be different, the direction of the change might be different, price might go up or down, but conceptually it's always going to be the same, right? So if all of this made sense, you are in great shape. If it didn't, let me know. Let me know if you have any questions. Otherwise, there is the full derivation of the demand curve. So thank you all for your time.